All right. Today we'll be discussing neural networks. My name is Madalisa, and I'm from the GCL chapter from Texas, and this is our fourth session in machine learning. So let's get started. All right. So I'll start by asking you guys what you think neural networks are, and I want you all to write your answers in the chat box to any of the hosts. All right, I got an answer from Abhinaya that says computers acting like our brain's neural network, like an electronic brain. And Adrita says connections like real neurons. Shridan says layers of things that makes decisions with biases and things like that to ultimately produce a conclusion. All these are really good answers. And all of these are actually correct. So, a neural network is a subset of machine learning, deep learning is a subset of machine learning, which is also a subset of artificial intelligence. So artificial intelligence is the all-encompassing concept that started off in the beginning, and then came machine learning that thrived later, and lastly, deep learning that's promising to escalate the advances of artificial intelligence to a whole new level. So neural network can be included in machine learning, whether it's like outside or inside the deep learning context. And one of the examples is when neural nets are used in a simple task-based learning, like to recognize car plates. All right, so this shows a difference between artificial intelligence, machine learning, neural networks, and deep learning. So artificial intelligence is an attribute of machines that embody a form of intelligence rather than carrying out computations. And machine learning uses a lot of data and then makes predictions. Neural networks, it uses algorithms and processes via signals and interconnected nodes. So we'll discuss what nodes, weights, and biases are. And deep learning is a form of machine learning that uses network of many layers. So deep learning uses neural networks and it processes information through that. So today we'll be talking about neural network, and before we go into what neural network is, I was thinking we should first go into what the brain is and what neurons are. And so what are neurons, and in what sense are they linked together? So neural networks are a set of algorithms modeled loosely after the human brain that are designed to recognize patterns. A neural network helps us cluster and classify, and you can think of them like a clustering and classification layer on top of the data you store and manage. So let's first dive a little bit deeper into the human brain. So our brain consists of 100 billion neurons or nerve cells. It's very complex, so I'll just go very brief on it. The brain weighs about 3 pounds and controls everything from our emotions to our decisions and our action. So the brain has 4 lobes. So this is the frontal, the parietal, the temporal, and the occipital lobe. These lobes are associated with certain functions. Over here is a picture of a neuron. As we go on deeper into how the neural network works, you'll see the similarities between the neurons in our brain and the neural networks used in machine learning. So this diagram consists of a dendrite, a soma, and the axons. So the soma is called the cell body that consists of the nucleus over here in the middle. And so the signals travel from the dendrite and down the neuron, which is insulated by the myelin sheath, which makes the signal travel down the neuron faster. And if you guys don't know what the myelin sheath is, just ask in the chat box and I can explain it further. But the axon terminal is then connected to the dendrite of another neuron, and the signals transfer from one neuron to another. So these dendrites completely branch off and the signals travel fast through one cell to another. And Shritan asks, there are lipid sheets on the axons, right? Yes, the myelin sheets are like sheets that insulate the axons that helps the nerve signals travel faster through the axon terminal. All right. So each neuron may be connected to up to 10,000 other neurons, and they pass signals to each other via 1,000 trillion synaptic connections. That's equivalent to a computer with about 1 trillion bit per second processor. So how do these synapses work? So this point of interconnection of one neuron with another neuron, that's called a synapse. And the amount of signal transmitted depends upon the strength or the synaptic weights of the connection. This will be very important when we learn about the weights in the neural networks. So the synaptic weights of the neurons, it depends upon the strength of the connections. And these connections can either be inhibitory, which means decreasing strength, or excitatory, which means increasing strength in nature. So a neural network is a highly interconnected network with billions of neurons and with trillions of interconnections between them. So imagine the possibilities, a machine that can mimic learning from experience with its neuron-like mind, and a machine that learns from its examples it sees instead of scientists having to program it and give it data sets. However, its shortcomings were quickly realized. A single layer of perceptrons alone is unable to solve nonlinear classifications patterns. For example, it can't really identify images too well. So there isn't a simple, cheap way of training multiple layers of perceptrons other than randomly nudging all their weights, because there's no way to tell which small set of changes would end up largely affecting other neurons' outputs down the lane. So this deficiency has caused artificial neural network research to stagnate for years. And then a new kind of artificial neuron has managed to solve this issue. What it did is it slightly changed certain aspects of the model, which allowed the connections of multiple layers without losing on the ability to train them. So if you can see this picture, this shows the dendrites, the axon, and the axon terminal, and this below models how the neural networks would be. So yeah, as you can see in this picture, this shows the dendrites, how the inputs come in, the summation, and the threshold. We'll discuss this in further detail in a couple of slides. So in this model, I'll actually ask you guys a question. Just say yes or no in the chat box. Do you guys remember what you had for dinner on July 1st? Any of you? No? Okay, I'm getting a lot of no's. So the main difference between humans and these computers is that humans can forget, but neural networks can't. Once fully trained, a neural net will never forget. So whatever a neural network learns, it's hard-coded and it becomes permanent. But a human's knowledge is volatile and doesn't have to be permanent all the time. So a computer, as shown in this chart, also uses silicon transistors, but our brain has biological neurons or nerve cells, and the computer has 1 billion bytes of RAM and trillion of bytes on disks, and the brain has 200 billion neurons and 32 trillion interconnections. All right. So this also shows another, this is also another chart which shows the difference between neural networks, the artificial ones, and the biological neural networks. So the artificial neural network actually, it's much faster in processing information. It responds in nanoseconds, while our neural network in our brain processes things in milliseconds. And artificial neural network uses serial processing, which is like 1 by 1, but biological neural network uses parallel processing. And of course, the artificial neural network is less complex, whereas, as we saw in our previous slides, our brain is highly complex and has a dense number of interconnected neurons. And the artificial neural network has storage that is replaceable, which means like new data can be added by deleting an old one, so their space can be conserved. But in our biological neural network, it has adaptable storage. And so now we'll look at this picture. If I show you this picture, our brain processes it, and we know that it's a dog. So it goes through our brain, and we know that it's a dog. But at the same time, if I show you this picture, you know that these two aren't the same. So a dog is definitely not a cat, and it's definitely not a tiger. So how does the AI do this? In 2012, for the first time, a deep neural network architecture called AlexNet managed to solve this ImageNet challenge, which is a large visual data set with 14 million hand-annotated images without relying on handcrafted or extracted features that were the norm in computer vision up to this point. So AlexNet beat its competitions by miles. So it recognized that this image on the left is a mite, this one is a container ship, this one is a leopard, these are cherries. And this paved the way for neural networks to be once again relevant. So what are neural network elements? So deep learning has a bunch of stacked neural networks, and these layers are made up of nodes. A node is like the neuron in the brain. So a node is just a place where computation happens, right? And it fires when it encounters stimuli, just like the neuron in our brain. So over here, as we can see, the idea is that, as I mentioned, synaptic strengths, like the weights, are learnable and control the strength of influence and its direction. For example, excitatory means positive weight, or inhibitory means negative weight of one neuron or the other. In this basic model, the dendrites carry the signal to the cell body, where they get summed. And if the final sum is above a certain threshold, the neuron can fire, which sends a spike along the axon like you see over here. And in this computational model, we assume that the precise timings of the spike do not matter, and only the frequency of the firing communicates information. So the modeling of this fire rate of the neuron with an activation function represents the frequency of the spikes along the axon. So this is kind of how a neural network element is modeled. So first we'll have an input layer, where no computation is done here. They just pass the information to the next layer. And a block of nodes is called a layer. Then we have the hidden layer over here. In hidden layers, this is where the intermediate processing or computation is done. So here they perform the computations, and we'll come to know what computations they perform in a couple of slides. And they transfer the weights, the signals, from the input layer to the following layer, which can be another hidden layer or the output layer. So it's possible to have a neural network without a hidden layer, but it's also possible to have a neural network with multiple hidden layers. Then here's the output node or the output layer. Here we finally use an activation function that maps to the desired output format. Okay, so let's use the same dog example. When we see this, when the artificial intelligence sees this, they take it into the input layer and it lights up. Then here are 4 classifications. It goes through something like quite like a dichotomous key. So it says if it has a tail, this lights up. And for the next one, if it has drooping ears, that lights up. And over here, they'll say something like if it's an amphibian, this lights up. So as you can see, the computer recognizes that it's not an amphibian, but it does have tail and has drooping ears. So these 2 things, they light up. And because these 2 things light up, the combination of those 2 things lead to other different classifications. And once all of these are classified, there'll be an output where you can find out whether it's a dog or whether it's a cat. So after this, we can see, I'm going to ask you all a question in the chat box. So in this equation, what is 5 and what is 2? Please let me know. Okay. Okay, I'm getting a lot of answers here. 5 is the slope, 2 is the intercept, 5 is the coefficient, 2 is the constant. Okay, what I was looking for actually, Alyssa said it. If 5 is the coefficient and 2 is the constant. Yes, 5 is the slope and 2 is the y-intercept. But Alyssa's answers makes more sense to use in this situation over here. All right. So I'm going to use this 5 and the 2 simile to explain weights and biases to y'all. So a weight is a parameter within the neural network. It transforms the input data. And a bias represents how far off the predictions are from their intended value. So the weights and biases are probably the most important concept of a neural network. When the inputs are transmitted between the neurons, the weights are applied to the inputs and they're passed into the activation function. So within each node, they have a set of inputs, weight, and a bias value. As an input enters the node, it gets multiplied by the weight, and the resulting output is either observed or it's passed to the next layer. Weights can be thought of the strength of the connection. Like I mentioned, the synaptic strength in the neurons, the weights can be thought of as the strength of the classifications. So weight affects the amount of influence a change in the input will have upon the output. So for example, a low weight value will have no change in the input, and a larger weight will have more change. So let me go back over here, and let's use the same dog example. So let's say I give more value to the fact of whether or not this animal has a tail. Let's say I give that about 3 points out of 5. And let's say I give the fact of whether or not it has drooping ears 1 point. So when I bring my input, I'm going to multiply it by the amount of the connection or the strength of that classification. And then it moves on to the next layer. And a bias will represent how far off the predictions are. So a bias is sort of like when you think that one of them is more important than the other one, you add that to the value you get. So as for weights, the weights are the coefficients of the equation. When we did 5y is equal to 5x plus 2, you can imagine the weights as the number 5. So the negative weights, of course, reduce the value of an output, just like the negative coefficient reduces the value of y. So when a neural network is trained on the training set, it's initialized with a set of weights. These weights are then optimized during the training period, and then the optimum weights are produced. So what the weights do is they reflect how important the input is. So this image also shows the comparison between neurons and the synapses between them. So the input goes into the neurons, and based on which neurons light up, they lead to a domino-like effect and triggers other outputs. So what is a bias? A bias is an additional parameter in the neural network. The bias is the constant, or the number 2 in 5x plus 2, which helps the model in a way that it can fit best for the given data. If there's no bias, or due to the absence of bias, the model will train over a point passing through the origin only, as you guys see on this left graph over here. And this is not like a real world scenario, but on the right over here, as we can see, because we have a constant, it's predicting more of what the real world situation will be like. It helps you learn the patterns and acts like an input node that always produces the constant value 1 or any other constant. So because of this property of biases, they're not connected to the previous layer. So here is the formula that we use to find out the output of the function. So the Greek letter you see here, that's sigma, that also means the summation of. So the weights are essentially reflecting how important an input is, and the bias is used to shift the result of the activation function towards the positive or the negative side. So if we can see here, if the inputs are x1, x2, all the way to x9, and the weights are W1, W2, all the way to W9. And of course, these are just variables. Then our weighted sum will be x1 times w1, x2 times w2, and xn times wn all the way. So that's the summation of the weight times the input. And then when you add a constant to that sum, you can add a bias over here. And then this value would be fed into the activation function, which then prepares the output. And then the activation function is like a mathematical function that normalizes the inputs. So if, for example, if I give you a value, of input like 2, and I give a weight as 3, and I give you the second input as 3, and I give you the weight as 4. So you'll multiply these values to their corresponding weights, and you will add them together, and then you will add the bias to that summation. And then you will plug it into the activation function, which again shows you the true output. So here's the summary. The sum of the products of the weights and the inputs is calculated in each node. So every node has the input, the weight, and the biases. And if the value is above a certain threshold, typically 0, it fires and then takes the activated value to the next part. So this is much like the way the neuron in our brain works. It fires an action potential only once it passes the threshold in our brain. So now we'll go into a little bit of details of the types of neural network. So this is one of the simplest types of an artificial neural network. So in a feed-forward neural network, the data passes through the different inputs till it reaches the output node. In other words, the data moves in only one direction from the first tier onwards until it reaches the output node. This is also called front propagated wave, which is usually achieved by a classifying activation function. So a feed-forward neural network are used in technologies like face recognition and computer vision. This is because the target classes in these applications are hard to classify. So the next neural network is called a recurrent neural network. It's a type of artificial neural network in which the output of a particular layer is saved and it's fed back into the input. This helps predict the outcome of the layer. So recurrent also used to refer to the two broad classes of the network with similar general structure. So one of them is finite impulse and the other is infinite impulse. Both of these exhibit like dynamic behavior. A finite impulse recurrent network is a direct graph that can be unrolled and replaced with a strictly feed-forward neural network, which again only works in one direction. So a recurrent neural network, I think in the next slide, it'll show you how exactly it works. Okay. So the first, let's program this. So let's say we input a word called machine. And in the recurrent neural network, it'll output the most likely next word, which will be learning. So the output so far, I want you all to look at the bottom of the screen here, which shows the output. So the output so far will be machine learning. And then it uses the memory of the previous word. So when you say learning again, it outputs is. And then when you plug in is, it outputs fun. And then that gives you to the output, machine learning is fun. So it remembers what it did, and then that is what influences its next prediction. I think there's a question in the chat that says, how does the computer know the biases and the weights? Are they inputted? So yes, both of these have to be provided. Like logic can be used, but typically it's programmed and it's provided to the robot. All right. So next, let's move on to the next neural network, which is called the radial basis function. So in recent decades, the power systems have become bigger and more complex. So this increases the risk of a blackout. So this neural network is used in power restoration systems in order to restore power in the shortest possible time. So for example, in the radial basis function, it considers distance of any point relative to its system. And then these are used as activation functions. And the next type of neural networks is called a multi-layer perceptron. So this multi-layer perceptron has 3 or more layers, multiple layers, and it's used to classify data that cannot be separated linearly. So this is a class of a feed-forward artificial neural network, and the term MLP is used ambiguously, but it sometimes loosely, it refers to any feed-forward neural network, and it refers to these neural networks composed of multiple layers of perceptrons. And again, the multi-layer perceptrons are used in speech recognition and machine translation technologies as well. Okay, the next type of neural network would be the CNNs, or the convolutional neural network. So the convolutional neural network has a variation of multi-layer perceptrons. So before passing its result to the next layer, a CNN layer uses a convolutional operation on the input. So CNNs show great results in semantic parsing and paraphrase detection. They're applied in signal processing and image classification as well. So CNNs are also being used in image analysis and recognition in agriculture, where weather features are extracted from satellites to predict the growth and yield of a piece of land. So these CNNs are really helpful to the farmers who can decide whether this piece of land can grow a type of plant well or not. So next we'll talk about the strategies of machine learning in the artificial neural network. So let's take an example. There are a couple of ways to build IKEA furniture. Of course, each will, if you do it right, they'll lead to a completed couch or a chair. But depending on the details, one approach will make more sense than the others. If you have the instruction material and all the right pieces, all you have to do is follow the directions. But if you get the hang of what's going on with the instruction manual, then you can set it aside and go solo. But if you misplace the instructions, which is very unfortunate, then it's up to you to make sense of that pile of planks and wooden dowels. So it's the same way with deep learning. Based on the kind of data available and the research question at hand, a scientist will choose to train an algorithm using a specific learning model. So let's look a bit deeper into what those specific learning models are. So this first specific learning model is called supervised learning. So in a supervised learning model, the algorithm learns on a labeled data set, and it's providing an answer key that the algorithm can use to evaluate its accuracy on training data. This usually involves a scholar. So for example, a scholar or a person has to give examples while preaching for the better understanding of the moral, right? In the same way, artificial neural network implements pattern recognition, where it starts guessing while recognizing. Then the trained patterns provides the neural network with answers. So if you can see this image, the supervised learning will predict patterns. Okay, so this is a duck, this is a duck, this is not a duck, the last one's also not a duck. And then when you give it another one, it can predict whether it's a duck or not. So if I give you another example by saying y is equal to the function of x, and the goal is to approximate the mapping function so well that when you have new input data, when you want to put in another x into the function, you can predict the variables y. So it's called supervised learning because the process of an algorithm learning from the training data set can be thought as of a teacher who is supervising the learning process. We know the correct answers. The algorithm makes predictions on the training data, and it's corrected by the teacher. So learning stops when the algorithm achieves an acceptable level of performance. So the next one will be unsupervised learning. So unsupervised learning, it comes to action when there's no sample data set with known answers. So in here, they search hidden patterns. This is where the concept of clustering comes in. It involves dividing the elements into sets of groups, and it's based on unknown patterns that are carried out using existing data sets. It also provides unlabeled data that the algorithm tries to make sense of by extracting features and patterns on its own. See, if you can see on this picture, so the ducks and the mouses and the bunnies are classified in different groups. So clustering is an unsupervised learning technique. And the goal of clustering is to find natural groups or clusters in a feature space and interpret the input data. So there are many different clustering algorithms. One approach is to divide the data points in a way that each data point falls into a group that is similar to another data point in the same group based on predefined similarity of distance in the feature space. So what is clustering? It's commonly, what is it used for? It's used for detecting customer segments in marketing data. So if you want to know the different customers who help marketing team approach these, for example, how does the gender of a person, their location, their age, their education, their income bracket make them or influence them in such a way that they want to buy your product. So unsupervised learning can be used to cluster these customers into these different groups so we can use them for further techniques. So the next one is called reinforcement learning. Reinforcement learning is a strategy built based on observation. So the neural networks takes a decision by considering its environment. If the observations are supposed to be negative, the neural network adjusts its data to make a different decision for next time. When we consider the example of a dog in the screen above, we have the owner of the dog and the dog, which we can name the agent, and the environment, which is the owner. So when the owner of the dog is present in the garden, he or she throws a ball. So the throwing away of the ball is the state for the agent, and now the dog will run after the ball, which is an action. So the result of this will probably be an appreciation or food for the dog from the owner. So this will be the reward given. And now the dog observes that it gets good rewards for catching the ball. So the next time when the owner throws something, it'll forward and it'll catch it again. So let's say the dog does something wrong in this spot and the owner gives it a punishment. Now, this is what reinforcement learning is used for. The dog realizes that it got a punishment and makes sure that it doesn't repeat the same action again. So, as I mentioned, an agent is the person who takes these actions, and the dog is the agent here, and an action is the set of actions that the agent chooses to do. For example, it's the dog who decided whether to go after the ball or just look at the ball and jump. And the environment, it's the surroundings of the agent in which it moves. In this dog example, the environment consists of the owner and the garden in which it's present. It's the environment which gives the agent its reward as an output based on the agent's current state and actions. So this page shows a summary of all the 3 different strategies of machine learning. So for example, supervised learning, it uses machine learning to label trained data, and it's told the correct output, and it compares its own output and adjusts its methods. And unsupervised learning, the data isn't labeled. The machine must figure out the correct answers without being told, and therefore discovers unknown patterns in the data. So now algorithms must be used for unsupervised learning so that they can find suitable patterns and structures. So reinforcement learning, it gives the machine the most freedom out of all the 3. They find suitable patterns and structures in the data on their own. And this gives you trial and error where you yield the greatest rewards. So now let's go a little bit into the applications of machine learning before we start playing our game. So here, applications of machine learning include neural networks, include image recognition, NLP or natural language processing, translation, and language generation. It's also used in drug discovery and development or stock market prediction. It's also used for chatbots and delivery driver route planning and optimization. So here are some recent advances and the future scope of machine learning. So fuzzy logic is a type of logic that recognizes more than just simple true or false values. I've written that over here. So it stimulates the real world. For example, let's say today it's really sunny outside. Might be 100% true if there are no clouds. It might be 80% true if there are a couple of clouds, 50% true if it's hazy, and 0% true if it rains all day. So the fuzzy logic takes into account the concepts like usually, somewhat, and sometimes. So fuzzy logic and neural networks have been integrated for uses as diverse as automated engineering, applicant screening for jobs, the control of a crane, and the monitoring of glaucoma. So another recent advances and the future scope include psychology and neurology, the common usage of self-driving cars, the composition of music, handwritten documents to be automatically transferred into the digital documents, self-diagnosis of medical problems, and so much more. So this is a quote from a writer, Howard Reingold, who describes a neural network. It's this kind of technology that it's not an algorithm, it's a network that has weights on it, and you can adjust the weights so that it learns. And you teach this through trials. So what I'm gonna do is, before we start playing a Kahoot, I wanna ask y'all to text me in the chat box, and I'll open that up in a couple of minutes, or I'll open it up, and I want you to text me what weights are, in your opinion, the weights in neural networks. So if y'all could tell me what in your simplest definition weights mean, so I know whether to like explain it deeper or anything. All right, so I'm getting the strength of connection between you. I think I have a question. Rishi asks, what type of machine learning models should be used to map the layout of houses and hospitals? Is that even possible? That's a really good question. I think you can use deep learning to map the layout of houses and hospitals, but at the same time, I don't think supervised learning would be part of it because you're supposed to give the set of data. And as for reinforcement learning, that's definitely not it. So it might fall into a little bit of unsupervised learning, but I don't think that falls into the category of neural networks at all for the layout of houses and hospitals. Okay, I get the relative importance of a data input. The weights are values that are multiplied by the input values to see if they meet a certain threshold for a certain response. Multiplying the points given to a node's value. So I think Aditi, Ellison, Abhinaya, Rishi, and Sridhan all answered it correctly. That's perfect. That's exactly what a weight is. And what about biases? Do y'all know what biases are? Could you tell me in the chat box? Okay, I got a couple of answers. Abhinaya says how much to shift it in the positive or negative direction. Aditi says adding a constant to a note's value to make it more important. Shridan says their biases are values added to the sum of weights multiplied by the input values that show how far off the prediction was to make it more accurate. All of these answers are correct. That is what biases are. And I think Shridan asked the question whether RNNs are used for autocomplete, and that is correct. RNNs are used for autocomplete because the recurrent neural networks, they predict what you've already written and they copy that onto your autocomplete form. So next, we'll be playing a Kahoot game, which I will share my screen soon. And let me get started on. I hope everyone's joined already, or if you've not, just let me know in the chat box and I'll wait a bit. All right, get started. Great job. Yeah, the neural networks branch off just like the dendrites in our neurons. Yes, that's correct. The training time depends on the size of the networks, and the neural networks can be simulated on a computer as well. Great. So Shridan, Aditi, Abhinaya, Goat, and Nitya is leading. Yep. So the neural networks have memory of the previous dates. That's what RNNs are. That's correct. Yeah, so okay, so deep learning is the subset that's based on artificial neural networks. Yeah, so all of them are an application of ANNs. Right. We actually have 100 billion neurons in our human brain. Billion with a B. That's correct. Great job. Yeah, so it was actually cell body on the neuron, not the nucleus, because it pointed to not the center part of it, but the whole thing. It's correct. Great job. Yep, that's an axon. Yeah. So neural networks can be used in all of them, including image recognition, drug discovery, and predicting the stock market. Yeah, supervised learning uses trained patterns, and unsupervised learning is what clusters these elements. And reinforcement learning is based on observation. Yeah, I kind of said that right now, but unsupervised learning is not based on observation. A good job, Shridan, Abhinaya, Aditi, Goat, and Goat. Great job. Yeah, a radial basis function is it has distance of any point relative to its center. It's called radial because it branches off like that. And I don't know if you guys remember, but radial basis function was used in power restoration. And 3 or more layers is multi-layer perceptron. And well, yeah, it's used in power restoration, not as much of image and video recognition. Great job. Yes, it's used in image and video recognition and natural language processing. Yep. Yeah, that's true. Deep learning is stacked neural networks. Good job. Great, yeah. That's correct. It's a parameter that transforms input data. The thing that shows the differences between functions output and input, that's your bias. Uh, I'm not sure why that didn't pop up. Okay, sorry. Okay, yeah, that's what it was supposed to mean. I don't know whether that was just my computer, you guys didn't see it either, but That's the formula for each node, and y'all should know that. That's the sigmoid function of weight times the input plus the bias. Great job. Good job. Code has 7 correct answers in a row. Yeah, that's correct. A node is a lot like the neuron in the brain, and that's where all the computation, like the formula you guys saw in 2 questions ago, that's where it happens. It does not show the difference between the input and the output, and it's not a parameter. It's not the same thing as weight, yeah. Yes, that's all of the above. Great. So in feed forward, yeah, I'm sorry, you guys. My dad walked in and asked me who GOAT is. So reinforcement learning is a strategy based on observation, and it's also the decision that's based on the environment. Great job. It's great. Yeah, multi-layer means 3 or more layers. Right, the bias is like the constant in the equation, and the weight is like the coefficient or the slope. Yeah, congratulations to Shreden, Abhinaya, and GOAT. Great job, you guys. All right. So now we'll be going into a little bit of Google Colab, which Ashley will cover for all of you. So Ashley, you want to take over?
Yeah, of course. Okay, so also like feel free to turn on your cameras, and I'm gonna be presenting on, we're gonna go right into coding. So I'm gonna be teaching about CNN. So we went over convolutional neural networks a little bit in that PowerPoint, but I'm gonna go a little more into depth. Let me share my screen. Okay, I'm gonna take a little bit. But yeah, if you have any questions, I know it's hard to see the chat when you are presenting, so just tell me. Like you always just interrupt me. I'm fine with whatever. Are you guys able to see my screen? Yeah?
Yes.
Yeah.
Okay. Yeah, because I seriously cannot see the chat. Okay, so I'm just gonna go right into this. So we're gonna be working with MNIST. So this is something that is developed by TensorFlow, and it has digits 0 through 9. So it can read all of these numbers, and we're using a convolutional neural network because that's usually what you use to read images and so forth. So I'm gonna go right into that. So I have this website. Oh, I already have it open, my bad. So I have this website and I really love it because it shows you how these layers work. So I'm gonna go ahead and just write a number in here, like 5, and it will go ahead and break it down. So it goes, okay, so I have this pixel grid, right? And it'll interpret it and go, well, the machine doesn't know what the number 5 is a problem. So it has to break it down into numbers, which it does know what that is. So it's breaking these down slowly and slowly until I don't even know what's happening at this point. So the thing that you have to emphasize or like make sure you understand in machine learning models is that they don't interpret things the same way you do. So you'll see that as it's broken down, it becomes something that's like a little one by whatever. And I don't really know how many are in that row, how many columns there are, except it will make it into what's called a vector. So when I mention a vector, just imagine this little strip. It's basically just breaking it down into these strips. So we're gonna jump into our program. And if you haven't used things like Keras and TensorFlow, it may seem a little daunting at first. Are you able to see this well? Yeah, I'm hoping. I know sometimes it can be a little hard to see it on.
Yeah, we can.
Okay, nice. So I'll go like right here. So don't worry about this right now. I don't expect you to memorize these, and especially when I'm explaining these things, don't get down on yourself if you don't know every single part because it gets a little complicated sometimes. I normally have to refer to things to be able to write these kinds of programs. So yeah. So the first thing we have to do is load our data set. So we could go ahead and do that through train X and train Y. So whenever you create a machine learning model, as we had said before, you need a set to show here's what my examples will be like, and here's what the results will be like of that set. And test is so we can see how accurate our model is. So it's kind of like you train it, it's like giving it homework, and then testing it at the end with an exam. And that's how you do it in a model. We'll just take a train and a test. So over here, you'll notice it says mnis.load data. So that's just us loading the data from Google, and Colab will go ahead and pull that. So we're gonna go ahead and summarize that, and this should take a little bit. And our train, it shows that we have 60,000, 28, 28, and that seems a little arbitrary right now, right? But you have to keep in mind that this is all relevant to the shape of our data. So we have 60,000 different sets on our training. So 60,000 different images that we are going to be training off of. And each one is on a 28 by 28 pixel grid. So it's gonna make a little grid that the computer can look at. And down here, it's the same thing, just we have only 10,000 because you want your test set to be smaller than your training set because you want to give it as much as you can and then just test it on the tiny things. So let's go into the next part. Also, tell me if I'm going too fast. I want to try to get through all of this within this time, but this will be linked after this and you go ahead and even test it out at the end. So we're gonna go ahead and take a look at what our data set even looks like. We can use a pyplot and it will create the rows based off of the current number we're at. You notice how it's in the range of 9. That's because we have 9 different digits that we are going to be reading off of. And it'll say, okay, so take my first 9 just as like a base. It'll just pull them randomly. So you notice how we have multiple ones. We have all sorts of numbers, and they're written sloppily. They're written different ways because you want to be able to account for every single circumstance you'll get, because no one's going to write a perfect 0. No one's going to go, oh my God, let me make this perfect. It's going to be a little sloppy, lopsided, and whatever. That's what you have to account for when you're training your models, that you have those sets that have images that are slightly twisted or maybe squished and so forth. So we went ahead and we made a C map, a color map, and it put on a grayscale. So it's just going to be black and white. And also a little trick is if you like hover over this, you could just see like what kind of parameters it takes. So if you go, wait, I know I'm supposed to use a C map, but what am I supposed to put in these parentheses? You can hover over it and it'll tell you, oh, here's the parameters for this. And if you read it, it'll go a little more into depth for you. So we'll go ahead and show it. And here's our results. And you notice how it's on the 28 by 28 pixel grid I was talking about. It just turned into a little image for our screen and displayed the first 9. Okay, so that was just like a little background to this. Now let's actually, oh my God, excuse me, actually create the model. So we have to load our digits and create an encoding for a 10-element binary vector. That's a mouthful. So let me just explain what that means. So down here, we're going to use our training set that we had declared up there, just like how we had declared up there, and load it. What we had done up there is just, I was showing you how to load it, but right here, we're creating the function that will actually load it and will run all of these functions. You'll notice how we declare multiple for our model to get the model to analyze all of our data. So we're going to go ahead and make our train data and then make it match a shape. And the shape is basically, what does our data look like? And you notice how it takes the first shape because every array starts at 0, and then it'll take the pixel grid. So it goes, okay, so this should be 28 by 28, and it's only 1-dimensional. So you should know your shape based off of what we did up here. If we didn't do this, you might have been a little confused. You notice how it printed out for me? God, that's perfect, right? It already gave me all the information I needed. So we could just go ahead and punch this in here. And you could go ahead and replicate this down here too. So we're gonna fill in the shape of our test data. Our test data is gonna be the same. Oops, yeah, train, gosh, if only I could type. Wait, this is our test X, so this is gonna be our test Y, my bad. Test Y dot shape at 0 is going to be the same shape because all of our data is the same exact shape in this model. So it's going to be a 28 by 28 and it's going to be 1-dimensional. So down here, excuse me, sorry, I have Slack notifications coming in. But down here, you'll notice that we use two categorical. It'll turn it into something that can be read as either 0 or 1. So we want to make this 0 or 1 so our model can just break it down. You notice over here, it's slowly breaking it down. This is exactly what we're doing right here. We're turning it into categorical data that could be read in only 0s and 1s instead of a long like array that's very complex. So we're basically trying to reduce dimensionality throughout this whole model. That means the number of parameters the model has to think about. So we're going to go ahead and convert that to categorical. And we'll return our train X, train Y, test X, and test Y. So now we have all of our loaded data in a 28 by 28 pixel grid that is now in 0s and 1s. So the next part is pre-processing. In any model you make, you'll have to pre-process the data. Whether it be for text, you're gonna probably filter out any commas or get rid of different, if it's can't, it would become can not. You have to break it down for the model is what I'm trying to get at. So over here, think of that for an image. We have to break down each pixel into its base numbers. So we can normalize the pixel value so it's within a range of 0 and 1. So how do you do that? if your range of pixels is between the colors 0 to 255, 0 being black and white being 255. Every image you see is made of tiny pixels, and each one is on this color range. So the model's going to go, well, 0 to 255 is a huge range, and that's very difficult to read. So we're going to go ahead and make it to zeros and ones, or binary. You'll notice a lot of the time these models will start going, let's turn it into the tiniest thing it can try to use. So that's exactly what we're doing. We're just converting the image into a readable vector. Vector as in this little line. So down here, we can do that through a program, and we're going to call it train norm. So we're going to say train.asType float32. So as of right now, our training and our testing are all integers. That means it's only 0 and 1. But we want this to be read as a float so we can divide it. I'll explain why we need to divide it. So when we do train underscore norm, it's going to be an integer right here, except we need to divide it by that color range of 255 to evenly spread it from a range of 0 to 1. So they'll range from, let's say it's 0, 0.1, 0.002, whatever, and so forth, right? That was just example numbers, not real numbers, but you'll notice how it's now kind of like on a little range, and the model will be able to see all of these float numbers, which are decimals, and understand them. So we're gonna go ahead and return that. Now we have all of our data pre-processed, it's perfect. And the model's like, great, I love this, it's from 0 to 1, and I will have a really easy time reading this. So now we're gonna go ahead and create our actual layers. So in your CNN model, let me just explain this. You need different layers so you can break it down. And this includes max pooling. And this sounds a little hard to understand at first. You'll get a giant grid of all these numbers. And just for example, this is not actual representation of our data, but this just gives a sample. You'll have all these numbers in this grid, and it'll take the biggest one, which it considers the most important. So it'll go, okay, so let's take 20, 30, 112, and 37. And it'll reduce the dimensionality, as I mentioned before, get rid of like numbers that aren't important. The model goes, I don't really need that. I only need this. So it only takes the best numbers it needs. So let's go down here. So when you are using a model, you have to define the activation function, how many layers there are, the loss function, and so forth. There's so many things. So over here, we're going to go ahead and create a model sequential. It will basically make this deep learning model. And we're going to go ahead and add a layer with a convolutional neural network that's only 2D. So it's not 3D, it's just a flat vector. And we'll go ahead and use the things I want to highlight here is the activation function and the kernel initializer. So what this means is, so we went over the activation function. It's something you use to kind of like level out your weights. So you'll notice that it's ReLU, but what's ReLU? Let me scroll down here. I have it all written down. And it'll take your neurons and it'll go, I want this one because it's the most important. And it only takes the ones that it values the most. So if it's a negative number, it'll go, oh, put it on the 0, it doesn't matter, I won't read this at all. But if it's anything from, let's say 1 to like 5 or so, it will go, okay, so this is kind of important to me, let me put it on this range that I will be able to read from. So this is important. There's all sorts of functions. You'll have one that goes like a curve. You'll have ReLU functions that will go below the graph and curve up. There's all sorts of them, like different functions that they'll use that have just been developed, and you can always choose which one you think is best. For here, we use ReLU. Normally with ReLU, you'll use something called a key uniform. So this is something that's a kernel initializer. So it goes ahead and it makes all the weights, and it goes, okay, let me just make it all uniformly distributed. What does this mean? It's just gonna create all the weights and go, okay, all of these are like unbiased. It makes unbiased weights for you. So it'll go ahead and make it, and then the ReLU function will go ahead and adjust it for you. So your weights will be perfect for your model, because all the model's doing is going, what's our weight right now? And let me adjust it so it's a little better and my accuracy is better. So we'll adjust it until it gets better and better. So we'll go ahead and apply max pooling, which we explained above. We'll go ahead and compress our data. And that's in just part of our model. We're gonna just add it to one of the layers. And we're gonna flatten it. So this is also part of reducing dimensionality. So this is normally used with CNNs. It'll create one long feature vector. So it's basically this. It will crunch it into one long vector that the computer's like, okay, that's super easy to read. It was in one kind of like an array that's like big, but now it's gonna make it only one dimension so the computer can read it all in one step and super fast. Because we're using ReLU, it's gonna be a very fast model, because it won't have to think about any of these negative numbers. And also because we're using flatten, it'll only have to think about one dimension of a vector. So just to like explain this, dense was used up here, and this will just help make all of our layers. I know I'm running low on time. Let me wrap this up real quick. Except soft, so let me just explain this a little deeper. So dense takes all of your inputs and it goes, okay, so where's my next output? And then it goes into the next layer and the next layer. And each of these layers are densely connected, hence why it's called dense. So each of these neurons are interconnected like they are in the brain. So dense just is a way to make a brain in a computer, basically. And then softmax will apply normalization. It'll just turn all of these numbers into probabilities that can add up to 1 or technically 100%. So go, okay, all these numbers are within a probability of having significance. And then we'll go, okay, so let me just put it in a range that the computer can read. And I'm not going to go into these as much because I'm running low on time, except basically we're using stochastic gradient descent. This is just when you're adjusting the weights. So it'll, oh my bad, sorry, I clicked on the text. Except anyways, it'll adjust the weights to fit your model. So it'll go ahead, let me click out of there. It'll go ahead and adjust the weights along this curve to make it perfect for your model. So think of it like a ball rolling back and forth. It'll go whoop, and then back a little less, until it lands right where it needs to be to have the perfect learning rate. Up here, we declared something that, we used SGD, which is stochastic gradient descent, and we had a learning rate of 0.01, which means every time it goes along that curve and it realizes, oh, I'm kind of wrong, it'll adjust it by a little bit. That's why it's 0.01. And then it'll say its momentum, which is going back and forth, is going to be a lot. So we're going to analyze the model using k-fold cross-validation. I'm not going to go into this super in-depth since I'm really low on time right now. So it'll divide it into groups and it'll go, let me analyze each of these groups individually. And k-fold will basically go, okay, so here's all of my results. I just divide it into groups and let me shuffle them and make it so that there's no bias whatsoever. My accuracy is rock solid. Like there's nothing that can say, oh, but it might be because of the way your data was arranged, or it might be because you had the data in a fashion that was not appropriate. So k-fold solves that for you, and it'll go, okay, let me shuffle all this and create multiple folds which it reads off of, which is multiple groups. So you can always look back on this. It's fairly straightforward. It'll essentially just use the model and fit it to the training and testing set and do validation. So it'll test it and then it'll have a different set of data that will say, okay, here's the actual results and here's how the model performed overall. And this is just formatting. It'll give you the accuracy, whether it's 98, 99%, 95, and it will go ahead and create histories and scores, which is basically just the results, and it will print them out. So down here, we just created a plot. This is pretty self-explanatory also. You could always just name this something simple, like this is our results for CNN. Normally it's something a little more complex that could describe it really well. But yeah, so it's just gonna show our loss, our value loss, which is part of the validation model. So it'll go, here's you want to refer to your val loss when looking at how accurate your model is. So this is like the overall analysis of your whole model. And blue and orange is just like, here's like what the color of these graphs are gonna be. And the same things replicated below is done for our classification accuracy and so forth. So we're gonna go ahead and run all of these functions because we didn't actually run any of these. And it will all be run under run test harness. And it'll go ahead and train it. It will prep the pixels. It will evaluate the model, and then it will summarize it, and it will show the final performance. So I don't have time to do this. It actually takes a really long time to train all of this. Any model will normally take a really long time. So it divides in, I just took a screenshot. When you go through this, if you want to run it yourself, you just have to click the play button on each of them and then click play on this and it will start it. And you'll notice these epochs coming up are these groups, and it will have it into these divided parts of the training set. And I'll go, okay, I have a really low loss here. This is really great results right here. And it has a low validation loss. And you notice how these are pretty close to each other. If they were really off, you would go, okay, something's wrong with my data, because that means the model has something where it's training it and it's receiving bias, and then it's going to validate it and it's making errors, trying to solve the same types of problems again. So here's our results. We'll just focus on accuracy for now. You notice how it's at 0.9996. That's extremely high. So normally models, if you have a really good machine learning model, it's normally 90 to 95, but this is a really good data set. Like this has so many different examples for the model to read. So this works extremely well. And we just have our little graphs of these, and it will show the loss right here, and it will show relevant to our training, like the first test through, and then our validation, which I mentioned, which is the final results, which we labeled in blue and orange. So this is done for accuracy also. You'll notice it's up to like 0.99, like we had saw up there. And that's basically how you will load your data. You'll create your layers, and you'll test your data, and you'll have to validate it. You have to, I really recommend creating graphs when you're looking at your data so you could just see it. Because sometimes it's really hard to see how your model's performance is and how great it is, which is, it's gonna be great. If you can't actually see it up close. It's really hard to understand just numbers on a screen. So yeah, we went ahead and went through that whole process. I will have this whole thing linked, and you guys will be able to access this and run it. It took me like 15 minutes to run this whole thing. It takes a while. So 15 to 20, I'd say. So yeah, that basically wraps up my little presentation. Sorry, I went a little bit over, except yeah, I'll go ahead and stop sharing. And yeah, that's just a little introduction to CNNs.
Okay. If you have any questions, let us know, or else thank you. Thanks, Ashley. That was really good.
Oh, thank you. Yeah, I was worried about it getting a little, oh, thank you for the person in the chat. That's really sweet.
Haha, that's sweet.
Yeah. Yeah, I don't know if that was too much at once. I tried to like break it down, but
No,
I
it
was
was
worried
good.
being that this was okay. Yeah,
I
thank you
still
though.
recording, one
Yeah, I
second.
really enjoyed